Hello everyone, now I will give you a brief introduction of our work. The Score Priors Guided Deep Variational Inference for Unsupervised Real-World Single-Image Denoising. We know that real-world noise frequently appears in various image processing applications, such as photography images, fluorescence microscopy images, and CT images. The main feature of such noise is that it is signal-dependent and spatially correlated. Therefore, it is significant and challenging to remove such noise. Nowadays, some supervised and unsupervised deep learning-based methods have shown promising results in removing real-world noise, but they suffer from data collection difficulties and model generalization issues. While single-image-based methods are more practical, they often show poor performance. Hence, our motivation is to develop a new and effective denoising method that only relies on a single noisy image. Recently, score-based models have shown the capacity to capture complex image priors. However, some methods relying on score priors for image denoising can only handle additive white Gaussian noise. Moreover, these methods generally require score networks and complex sampling strategies for posterior sampling. To this end, we propose an effective and practical score priors guided deep variational inference for unsupervised real-world single-image denoising. Moving forward is our main method. We can first consider this general image noise model. I equals Fox, and under the Bayesian fashion, the image denoising task is to find the posterior distribution of x given I and also its estimators, such as the expectation. We often use the variational inference to find a trivial distribution to approximate the true one. The elbow function is adopted as the optimization function. Before we introduce our main contribution, we shall introduce the relationship between scores and the Gaussian denoiser. Following the existing works, we can easily obtain such a relation stated by Theorem 1. It says that the score function is directly related to the ideal denoiser for structured Gaussian noise. If we consider the diagonal Gaussian, we can get the simplified version. That is to say, the score priors are available from well-trained Gaussian denoisers, and we do not need to train the score networks. Based on such findings, we can utilize score priors to facilitate elbow optimization. In particular, regarding the latter part of the elbow function, we can use the Monte Carlo integration to get its approximation. For this approximation, the former part can be made analytical as key is chosen as a trivial distribution. Regarding the latter part, we do not need to explicitly expand it as traditional methods did. Instead, we can directly compute its derivative to x, then you will find the scores. We can therefore replace such scores with the equation marked in red and derive our main results. It is straightforward. We can find that under the guidance of the Gaussian denoiser, the optimization of the elbow function is adaptive, and we do not need to design additional sampling strategies. Apart from the score priors, we also designed the non-ID Gaussian mixture model to approximate the real-world image noise. We use phi and omega to denote the precision and mixing parameters. As the noise level of the real is varying, we cannot assign them fixed values. We therefore introduce hyperpriors for the phi and omega to specify our prior belief about the noise. To facilitate the elbow optimization, we choose the posterior distributions with the same forms as the priors. Then we can derive our full loss function. It consists of 5 parts. The lone L3, L4, and L5 are all analytical by design, so we can directly obtain their derivatives. Regarding the loss L2, we can incorporate our main method and get its derivatives through the scores from Gaussian denoisers. To provide the regularization to these variational parameters and further speed up the convergence, we adopt 4 CNNs to model these variational parameters. The whole diagram of our method is shown in this figure. Regarding the implementation details, we use the bias-free D and SIN as the denoiser to obtain the score priors. We train multiple denoisers on different clean data sets. As for the optimization, all losses except L2 are expressed as scalar functions in PyTorch. As for L2, we implement a customized class from the torch, autograd.function, and return the gradient in its backward function. The quantitative comparison is listed in the main table. Our method outperforms single image-based methods in most datasets. Our method is also comparable with some dataset-based methods in some test sets. Note that we just require a single noisy image while these methods require noisy datasets. Some qualitative comparisons also show the superiority of our method. We also give the denoising process of our method. It shows that it also can estimate the denoising uncertainty, which is important to safety-critical applications. That's all. Thank you for your listening.